Hello and welcome to Clean Talk. I'm your host, Brad Whitchurch. Today is Wednesday, July 20th, and it's 3 p.m. Eastern Time. And that means we're coming to you live. Very excited to have our guest on the show today. Dr. Norman Horn is a PhD in chemistry. He is an expert in antimicrobial technology and ultraviolet radiation, a research and development chemical engineer at Seal Shield, and a recurring guest on our show. Dr. Horn, welcome back to Clean Talk.
Thanks, Brad. It's great to be here.
Well, we're glad to have you. And the reason we wanted you to come back here today is because there's been so much advancement in ultraviolet radiation in a very short period of time. And we wanted to have you back on the show to tell us a little bit about that and what you're seeing in the marketplace. To what do you attribute this rapid development, and what are you seeing in the marketplace?
So there are a few reasons why we've seen a pretty dramatic shift overall in the landscape of UV technology for healthcare. The first biggest reason, of course, that everybody would expect is COVID. COVID really just brought everything down to its knees and revealed some prescient problems in infection control, even that UV technology is poised to, at least if not solve, then definitely assist in helping to solve. Infection control in general, I mean, that's kind of the point of Clean Talk, is a multifaceted problem. It's not any one thing that solves it, but rather a multitude of different solutions used in correct ways, implemented in smart and wise manners in order to make for better healthcare in general. But COVID really did expose a lot of stuff, of course, and the rise in UV was kind of almost expected at that point, in part because UV energy is really good at killing coronaviruses. Early on, we didn't even have that much data specifically around SARS-CoV-2, but as time went on, and now the data is in at this point, and it's pretty clear that in fact you need less energy in order to kill or inactivate coronaviruses, as comparatively to many types of other bacteria, whether we're talking gram positive, gram negative, and of course the more spore producing bacteria such as C. diff. The energy required to get at coronaviruses is much lower. And so there was this incentive pretty early on, just almost intuitively, that was going to be a thing that we needed to investigate. Of course, there was also the drive to try to assist in the reduction or in the issue of PPE extension, lifetime extension. And so the use of UV even to try and disinfect things like N95 face masks and various other types of PPE was really, really important early on. And so even we at Seal Shield were trying to assist in that with our technologies here. And there's to varying degrees of success. This was all something that, of course, was very time sensitive. And so while we did help in that PPE issue at the time, we're kind of beyond that at this point. And so now we're looking to different uses of UV in the healthcare environment to continue kind of building that momentum and using UV to have better healthcare outcomes.
Well, I want to talk about some of the recent innovations in UV. So much has been happening so quickly, but to your point, COVID really a catalyst for additional research around ultraviolet radiation and the viability of it as a solution to help reduce cross-contamination infections, specifically COVID. And we're going to talk about some of those products that are on the market today and whether they all do what they say or not, and what to potentially look for in a solution and what to maybe be wary of. But before the development happened, and this has happened in a very short period of time, but before there was the development, there was enhanced research, right?
Yeah.
So as a result of COVID, a lot more research being done around ultraviolet radiation as a solution. I know that you are a active member of IUVA. Can you tell our audience a little bit about IUVA? What is that, and why is that important, and how is it contributing to research and development in this field?
Sure, yeah. IUVA is the International Ultraviolet Association, and it is a non-commercial. It's a nonprofit that is dedicated really to enhancing our understanding of UV technology in the marketplace, and that in various capacities, not just healthcare, but also even water disinfection, for instance. but there's a big segment of IUVA that is really dedicated to healthcare research and also to standards development. And so IUVA, in fact, just before COVID really kind of got going, in fact, we were hosting some conferences to talk about the upcoming advancements of UV in healthcare. And as a result of those two conferences that we hosted in early 2020, as well as kind of the rise of COVID itself, there was this interest then in not just memorializing that in the form of, say, conference proceedings, but rather developing like a special section of some, and we were looking at all sorts of different options, but like what we ended up with was a special section of the Journal of NIST Research, or the Journal of Research of the National Institute of Standards and Technology, for UV technology in healthcare. And this is really special for a number of reasons. One is that, of course, it was memorializing these excellent conferences that we did. Two, it really was precipitated by and was related to the rise of COVID and the interest that there was in trying to use UV to help mitigate the COVID-19 pandemic as best that the technology could. And three, there had been nothing else done like this for pretty much the last 10 years. And so that led to, one of the strangest things I think I've seen in recent scientific memory in terms of publications, and that's that the Journal of Research of NIST doesn't normally even accept outside submissions. But in this case, they made this grand exception. And it was very exciting to see the response literally all across the world of people who were doing research in UV and bringing that to the forefront. There is no academic journal or research journal that is peer reviewed that is dedicated to UV research and technology. It just doesn't exist. And in fact, as I mentioned, there really hadn't even been a collection of papers that might call the advancements in UV tech for about the last 10 years. And so being able to be a part of that was really exciting. And in fact, that research now, we decided as the kind of the internal committee, managing that section, that we really wanted to take it and make it into a book as well. Now, to be sure, you can read everything that was in that journal special section for free online right now. You can just, Google search the Journal of Research of NIST, and you can read every single thing in that section. But there is something, to be said for having a physical item that you can slap on somebody's desk and say, look, this is the latest. Can you?
Well, I think you're aging yourself there, Norman. I think people of our generation may feel that way, but it is a significant that they put this journal together with outside peer review papers, and that now it has been published as a book. And I know you co-authored a couple of the papers that made it into the book, which I guess is now the UV Bible, so to speak. But can you tell us a little bit about your contributions to the journal?
Yeah, for sure. Although I wouldn't exactly call it the UV Bible. That is a title that goes to a different book from about 15 years ago, but we won't get into that. But there are some really important papers in this book that are more, I would say, far more important than my own contributions per se to the book. But a couple of things that we did, that I was part of in terms of co-authoring papers was that I co-authored the lead paper, which was really about setting the stage and identifying both the standards and technology and metrology needs that we're going to be needing over the next decade or so. And that was interesting to do. It kind of again memorializes what all of the things that were going on at the time in a way that kind of sets the stage for what was going to be presented in the rest of the book, or the rest of the section and the rest of the book, for that matter. The final paper was a kind of missive that we wrote together regarding the proposing a consortium of sorts for the industry today in order to advance more UV research from both the basic level in a pre-competitive environment and in a way that would help, again, advance the types of needs that we identified from the beginning, that we talk about throughout the course of the book, and that would then, we can then progressively move forward with things like government agency involvement, academic involvement, and industry involvement all together in such a way that is a collaborative effort, as opposed to just all of us being out on our little islands and attempting to, randomly do things.
So when you say a consortium, do you mean like IUVA, or even more multifaceted than that?
IUVA is an educational organization, if you will. The consortium would be dedicated more toward the solicitation of funding and the promotion of the actual research itself. So IUVA won't sponsor projects like that. For instance, it won't give a grant to a professor, at least not right now. Maybe IUVA would be involved in such a consortium as an educational organization with an interest in the advancement of UV tech, but it wouldn't be the same thing exactly. Industry consortiums, usually are directed towards different types of aims, if you will.
Well, I think it's significant that NIST is the one who really, I guess, published the journal, and that's the National Institute of Standards and Technology. And I feel like in UV, we need some standards. So I assume that was what prompted this work. And how are we going to be able to use now the standards that have been identified or developed? And how do you think that those get utilized, whether it's regulatory or within competitive industry?
Yeah, you could identify that there's probably three areas in which standards, and there's more than three areas, but we'll just talk about three, where standards are kind of needing to be established right now. One is the metrology itself. So how do you measure the output of UV devices in a standardized way that anybody can then look at and understand if you're, someone with nominal knowledge of the art per se. And so that itself is kind of a challenge sometimes because different types of sources have different types of outputs. Whether we're talking about LEDs, which have a very tight wavelength range of emissions, versus, say, a mercury lamp, which is a broader spectrum source but has very strong emissions in certain areas because of just the way it's designed. You have xenon lamps that are pulse-based as opposed to more of a almost what we might call a black body output of light. And so you have different types of sources with different types of needs and measurements. So there have been some standards that are still somewhat still in process, but are going to be kind of online, if you will, over the next year or so. I think it's LM86 is one of them, and just for denotation's sake. So you have that type of the metrology element that we just need to be able to measure the light better, and that would be for creation.
And that, as you said, that helps to compare different types of sources, and make a level playing field around different solutions. So with these kind of standards, we can weed out kind of the viable solutions versus products that use UV light but may not get the same results.
Yeah.
If you're using UV light, I mean, is all UV light the same?
Well, I mean, a photon is a photon is a photon, as we like to say in IUVA, but the sources are very different. Where like we mentioned, LEDs would be very tight wavelengths, but others are much more broad based, and so they'll have multiple major spikes in various wavelength ranges, where you have high intensity versus low intensity elsewhere. So all the photons are the same, the ranges are defined, but the sources behave differently because the only way you can even create this kind of light is through jamming energy into atoms and then making them emit light from that. I mean, that's always what we are doing when we're creating light sources. Even the sun does that, right? But there are, I think it's more that the sources are different than that there's differences in the UV. There are
and the results are different, right? So not all just because a product has UV doesn't mean it will be effective. It depends on the source of that UV and how it's utilized, right?
Yeah, to an extent. I mean, if we just say, oh, you have a UV source, well, what we really mean when we're talking about germicidal UV is a very specific wavelength range. In fact, some products that you'll see out there were marketed even during the pandemic as being, oh, this is a UV light device that's going to kill, it's going to kill stuff and bacteria around you. But it was using essentially what might amount to like a black light bulb. To where instead of using germicidal UV light, which was sub 300 nanometers in the UV spectrum, it's producing light in kind of the way over 300 nanometers as its primary wavelength. It's not going to do a dadgum thing to any bacteria. The only thing it's going to do is if you shine it on your body, it's going to give you a little bit of a sunburn. That ain't worth it.
And these standards that we've developed to help differentiate between these type of solutions, how do you envision those being applied to whether they're healthcare grade products or consumer products, so that the buyer doesn't need to beware, I guess, that what they're buying is achieving their goals?
Yeah, that's a great question. It's going to take some time to get there, but one of the great things about kind of our industry system, which includes varying types of organizations like IEEE and whatnot that certify things, is that these standards for measurements will be kind of loaded into other types of standards and certifications. So you would be able to say, for instance, that thus and such a source is rated for this type of capacity, and it's certified under this standard, and you can reproduce that at that point. And that's really what it comes down to, is that these standards help us to be able to reproducibly measure that which somebody is selling to us. And so for healthcare to be able to see that, oh, well, this follows the industry leading set of standards, is really important to giving confidence that they are getting what they think they are getting. And so people who are good actors in these types of scenarios, groups like Steel Shield and others, are going to be very interested in adhering to these industry standards in order to demonstrate that, yes, we've done our homework. And that's really important for any type of industry, is why any industry decides that they want to follow standards to begin with. So that's really exciting, because these sorts of things didn't exist. And that's just for the light production component of it. The next part of that, after that, is efficacy standards. A lot of the experiments that are used to validate whether or not your source is actually inactivating the bacteria or the viruses correctly and to a certain dosage, if you will, are based on other types of ASTM experiments, standard types of experiments that were never designed to try and deal with kind of the UV space. They're much more generic, or maybe they're directed towards, well, this is just a surface disinfection type of ASTM standard that we're adhering to, as opposed to something that is specifically written with UV in mind. And so that's going to take potentially even longer to get there at this point, from kind of a standards writing perspective, because there does need to be kind of a meeting of minds of people who are in academia, who've studied this stuff extensively for years, industry who's creating varying types of sources and has an interest in trying to get to the accuracy that's required in order to demonstrate that their products work, and so on. But I would anticipate that we're probably looking at least another couple of years before we see that really take the place of what's already existent out there in the marketplace.
But the ball is rolling. The standards are evolving and being developed as a result of the COVID catalyst. And there's been tremendous development in the ultraviolet space. Can you talk a little bit about what you're seeing in the marketplace and any predictions for emerging technologies within ultraviolet radiation?
Yeah, absolutely. There are some really cool things just from a pure technological standpoint that we are beginning to see. One is the rollout of what it's called far UVC technology, or far UVC sources. What's really interesting about this is that, well, let's define what that means first. So normally, when we talk about UVC lamps and the wavelengths that are used in order to kill bacteria in those circumstances, we're talking about like mercury lamps, which have a peak at around 254 nanometers, or we're talking about xenon lamps that have about the same, or we're talking LEDs that range from anywhere from 254 nanometers up to about 280 nanometers in wavelength. Far UVC is basically ranging from 200 nanometers to 230 nanometers. What's significant about that, you might ask? Great question, Brad. I'll tell you. At 222 nanometers, we have the capacity to produce light at high intensity using certain types of compounds that we call exomers or exaplexes, and filtering out all other wavelengths. And so you have a virtually monochromatic source at 222 nanometers that has the capacity to inactivate bacteria and viruses while simultaneously not causing any type of skin damage or eye damage. Now that blew my mind when I first started hearing about this about 2.5 years ago. But the fact is that the research is now showing that that's pretty much true. That there's that really that light does not have the capacity to penetrate deep enough into your skin to really cause any type of DNA damage or skin or just burn damage. Essentially, I mean, it's kind of like, you know, when you go out in the sun for too long, you get sunburned, right? And it's because of UV. Well, there's also stuff that happens with UVC if you allow it to, you know, penetrate your skin for very long. It's not good for you, you know, but it's not. But what's when you get down into this far UVC range, you don't see that anymore. It doesn't even penetrate through the tear layer of your eye. And thus, what this enables is potentially constant exposure in a, say, hospital environment where you can just put lamps like above your head and you can be continuously disinfecting in an area. And so long as that research continues to hold up and be true, we will almost undoubtedly see applications where that's going to come into play.
Well, in fact, there are some products coming to the market today. Yep. I don't know if you know much about them and whether they're viable or not, but what are some of the limitations of far UV that our audience should be aware of?
Well, yeah, I mean, some of the limitations are simply that right now it's really expensive. And I think that's going to be a limitation to, you know, broad deployment off the top, is that the sources, you know, are they're just expensive to create. And so we may not necessarily see just wide dissemination right now, but similar to the way in which we've seen things like LEDs become cheaper and cheaper and cheaper with time, I do believe that was going to probably hold true for any given type of source like this, where, you know, the price per lumen or per energy output unit is going to go lower and lower until it becomes viable to just put it wherever we want.
What about distance and energy? Is that a different issue with far UV, that you need to have it closer to have the energy be effective, or is that just inherently an issue with UVC in general?
Well, you're kind of referring to, you know, the way that energy drops off with the when you have a light source, the energy of it kind of it starts off being, you know, very strong at the source, but as it is expanding in its reach, well, then the density of that energy is dropping off, and that's dropping off at with an inverse square law. In other words, that if you go twice the distance away, then you have 4 times less energy. And so that is a problem, but it's not so bad when you think about it in this case, because you're just constantly bringing more energy by just leaving it on all the time. It's not like what we would do where we have this issue of what we're only going to be exposing for just a little while, and so we have to be careful about how much dosage there, you know, that it gets at, you know, at various points, say with the UV robot to that effect. But if you're leaving it on constantly, you get a kind of a better result there overall. So it is an issue, but it's relatively overcomable, and especially since we don't really have to worry all that much about human exposure in the case of far UV, I think it's pretty exciting to consider that this could be a very good answer to a lot of issues with, say, you know, airborne viruses, you know, hanging around a hospital, you know, causing pandemics or something like that. Yeah, it makes a lot of sense.
Absolutely. Well, we've been talking about far UV for a couple of years now, at least, and now we do see some products starting to come onto the market with that emerging technology. What other innovative applications of UV radiation are you seeing come into the market, or that you can foresee coming in the future?
Yeah. One thing that I'm actually pretty excited about, and is kind of we'll call it an oldie but a goodie, and that is upper air UV technology is getting kind of a resurgence right now. And it's a very simple technology. The idea is to simply take the headspace of the air above your, you know, above where people are walking, and irradiate just that zone with UV. Just standard UV lamps, like things like, well, you can use LEDs, you can use xenon lamps, you can use mercury lamps there. And the reason for this is that because of the way in which air circulates in a room, when people breathe, and if say they're breathing out microorganisms, at least somewhat, that warm air is going to tend to go up, and then it can get disinfected up there. It's actually really remarkable that as long as you kind of have a constant source like that, and you can ensure that there's not much reflection to where there's no real risk of human exposure, you get essentially the equivalence of air exchanges that HEPA filtration and the massive air exchanges that are in hospitals, for instance, will get, with a relatively small source. And there are some limitations to it, of course, but the advantage to something like this is that it's much more easily manageable than a lot of other types of technologies, and it's extremely simple to implement. And moreover, it's been proven effective for literally 80 plus years. There were studies and incidents where, up to 80 to 100 years ago, there were installations kind of like this that helped to reduce tuberculosis in certain types of hospital scenarios, as well as the mitigation of measles in schools. And so when I just started discovering this stuff, I was actually really surprised. Like, why aren't we talking about this all the time? This is fantastic. And this is in fact why it was these types of things that one of the and I can't remember the name off the top of my head, but there was a Nobel Prize even given for UV technology in the first half of the 20th century, because this was such a powerful effect. It was just really fascinating. And I think there's a lot of interesting promise for implementing this type of technology as an additional measure for kind of constant disinfection of spaces that we're going to see really to come to a head, I think, in the next couple of years.
Well, and it's about time.
Yeah.
The standards are HEPA filtration, as you mentioned, positive and negative pressure. And a lot of people don't think about it, but a HEPA filter is just that. It's a filter, and it can only filter out down to a certain particle size. And most of the pathogens we talk about as being risk factor pathogens in healthcare are smaller than those particle sizes. And HEPA filtration does nothing to eliminate organic pathogens in the air, whereas UV has the potential to do that. So I would agree with you. I expect we'll see even more solutions that combine effective filtration with organic eradication.
Yes, sir. I think this is really exciting for us, is just because there's any number of places that will benefit from using this type of technology. Wherever you have large public spaces where you expect to see a lot of people coming in and out, if there's a risk of transmission in those types of spaces, then there's a clear advantage to having something like this available to you and having it in your arsenal.
Well, we talk a little bit on this show about the silver linings of COVID.
Yeah.
I would kind of check that box on this discussion, right? COVID has really been the catalyst for a lot of the research and development, the development of standards, as you talked about, and now the escalation of emerging technology solutions to help us in our fight against deadly pathogens. Dr. Horn, I know that you're active with IUVA. You gave them a plug. I know they have a conference coming up. What can you tell us about that?
Yeah, well, if you're interested in learning more, whatever industry you're in, the IUVA can probably help you out if you want to learn. Of course, www.iuva.org is where you want to go to learn about that. And we have an upcoming conference coming up in September 26th through 28th. That'll be in Cincinnati, Ohio. And you can learn more about that. Sign up to get there and learn from everybody who's going to be participating. There'll be researchers there. There'll be industrialists and plenty of technology to observe. There will be sort of a miniaturized trade show, if you will, with tables, people who are displaying different types of instrumentation, UV robots, measurement devices, radiometers, and of course, other organizations like NIST will be there presenting as well. We'll probably even have some regulators who will be present to talk on panels and whatnot, and be able to see like what's happening in the regulatory world, because that's definitely kind of an issue right now too. But again, that's September 26th through 28th. It's in Cincinnati. This is the IUVA Americas Conference, and I'm sure that if you will look in the show notes here, you'll find a direct link there, but if you just go to iuva.org, it's pretty prominent up there as a big old picture inviting you to come see us all.
IUVA.org is the place to register. Our guest today has been Dr. Norman Horn. Appreciate you being on the show. If you enjoyed our show today and want to watch some of our archival episodes, be sure to go to the Clean Talk YouTube channel. And if you want to watch us live every Wednesday at 3 p.m. Eastern Time, be sure to register to be a part of our community at cleantalk.tv. And until next time, for my guest, Dr. Norman Horn, I'm your host, Brad Whitchurch, reminding you to keep it clean.